Hi, everybody. My name's Alex Bowers, and welcome to Cluster Analysis in the Data Science Methods for Digital Learning Platforms. I'm excited to have you today. My name's Alex Bowers. I'm a professor of education leadership at Teachers College, Columbia University. And I do a lot of research with cluster analysis and especially cluster analysis heat maps. Some of it in digital learning platforms, others in different areas of education research. And so I'm excited to talk to you today about cluster analysis and cluster analysis heat maps and show you a few different applications from the research literature and then how to do it for yourself in your own research in our using your data. So the way that we'll work the following videos in this course is we'll have a few videos that you'll be able to watch. You can watch them each one after the other, or you can also take your time if you need to. There's a few different readings that are listed on the course website. And in addition to that, I'd also like to point out that there's a few other readings that you can get to as we'll talk through this. So welcome. So the reason I'm really excited to talk to you today about pattern analysis with cluster analysis and especially cluster analysis heat map data visualizations is that as we go through this section of the course, talking about cluster analysis, first, I'm going to give an example of hierarchical cluster analysis heat maps just to show you what it looks like from my research. So I'm going to give an example using non-cumulative grades and throughout the K-12 process in the United States to examine being able to look at who's going to fail to graduate or drop out from high school. Then I'm going to give you an example of using cluster analysis and this visualization process to look at clickstream log files from Canvas to examine engagement and participation of students. And then also look at the number of times students retake an Algebra 1 summative assessment and how many times looking at the clustering and finding groups and patterns of students who take and perhaps retake an Algebra 1 summative assessment multiple times. So that'll be one of the first videos. And then as we go into the second video, I'll talk about the background around cluster analysis. So looking at cluster analysis versus classification, machine learning versus inferential statistics. So looking at first clustering, both hierarchical and what's known as k-means versus classifying, such as k-nearest neighbors, support vector machines. There could be some confusion between these concepts. So we'll talk a little bit about that. Then we'll talk a little bit about unsupervised empirical clustering, which I prefer, and I'm going to really push for in these videos, which would be a bottom-up approach, versus k-means, which we'll talk a little bit about, which is really making it up in a few different ways. You select a number of clusters a priori, and then place it on your data and force it into those groups. Both can be useful in different ways, and I'll show you a little bit of both. But I'll show you mostly from the research literature on what it looks like when you use empirical clustering and hierarchical cluster analysis using this bottom-up approach. And of course, we'll talk a little bit about this idea that in cluster analysis, there is no agreed-on method for the correct number of clusters. And throughout the readings and these videos, you may be asking yourself, really? There's no agreed upon way of defining the correct number of clusters? Yes, really. And so we'll have a few readings on that. And I'll direct you in the videos to some other research that's out there. But also then I'll take a brief tangent into latent class analysis versus cluster analysis, where in latent class analysis, you actually can identify significantly different groups or clusters of responders or items. And you can really be able to you have a hypothesis test on the different types of groups, and there's distributional assumptions. So I'll talk a little bit about that versus cluster analysis, which I encourage you to really think about as being more of a descriptive technique. And then I'll give some examples of hierarchical cluster analysis heat maps using different distance metrics, such as Euclidean versus uncentered correlation. Uncentered correlation I really like, as it gives It has some benefits that other distance metrics don't. The agglomeration or clustering algorithms, such as average linkage, which is really useful when you have a lot of missing data. And then really looking at heat maps and cluster analysis and the research literature on visual data analytics. Then in the final video, we'll dig into a recent paper that I published in which I give an example using public data on using cluster analysis heat maps and grades. And then it has a linked tutorial on our full R markdown using the Motor Trend Cars data set that's inside R already. Now I'll walk you through not only that paper from 2022, but then looking at data cleaning, how to plot a hierarchical cluster analysis heat map, how to cluster using first Euclidean distance and then uncentered correlation and average linkage, and then add annotations, covariates and distal outcomes that you think are interesting. And so hopefully by the end of these videos, you'll have both the background, the readings, and the knowledge, both from the readings and the theory and the calculations, but then also the R code so that you can do this method for yourself with your own data. So let's get started. So there's a few different additional readings that I just want to point out here at the beginning. I'll talk next about this 2010 paper that I published that uses grades. And we'll talk through that next. But then this 2020 paper by Jorian et al., including me, uses museum data and students who walk up to a museum exhibit and whether or not they use it in a collaborative way. And we pattern how the students use the museum exhibit. The Nitkin 2022 piece uses hierarchical cluster analysis heat maps to look at a technology-based personalized instructional model. I'll talk about the Lee and Record piece in a few videos. That's using Canvas data and clickstream log file data to look at patterns of different usages. And then the reverter piece is quite interesting using course evaluations of cluster analysis. So let's talk a little bit and start first with where I usually like to start these kinds of conversations. So I really like this paper by Cattell in 1966. So we'll go back in time a little bit and think about Cattell's data box. So in this paper in 1966, Cattell had this idea that let's think about data as a data box. So you can have variables on one axis, persons on another, and then occasions on the third. And if we take different slices of the data box, the way Cattell liked to think about this is that if we maybe we look at just one person, but over multiple variables and many occasions, well, this is what clinicians like to think of as a diagnosis. And then if we take a different slice, though, what if we just pick one variable? Well, we've got lots of people over multiple occasions. Well, that's what educators like to see in growth, like in mathematics or in English or reading. And then the third slice that we can take might be where we have one time point. So all the occasions are the same, but we have multiple people over multiple variables. So this would be cross-sectional data or panel data. And policymakers like to look at interventions. Well, what if we want to take the entire data box at one time? Well, let's use cluster analysis heat maps, and we can see what that looks like all at once. So what I like about cluster analysis and cluster analysis heat map visualizations, before I show you an example, which the example is coming up next. But what I like about this is that for your research questions, you've got really strong possibilities of saying questions like, to what extent are there similar user data patterns? What do the data patterns look like? What does each data point for each individual look like, patterned in context with all of the other data? And how do the clusters relate to covariates and distal outcomes? So the method that we're going to talk through in these videos is cluster analysis. And I consider cluster analysis to be a descriptive statistic. One of the reasons why is there's no hypothesis test and no agreed on method for the correct number of clusters. There's few assumption violations though, and it's very robust to a wide range of data types, which is really nice, a feature when you've got lots of different kind of data. It also attempts to use all of the available data, and it's robust to missing data values and missing data issues if you use average linkage, like we'll talk about in a few videos. And then, as you'll see, the data visualization of clusters that we'll talk about are cluster analysis heat maps, which are adapted from bioinformatics and cancer biology. So, just a quick definition, you might be asking yourself, what is he talking about? What is this cluster analysis heat map thing? Well, this quote from Wilkinson and Friendly, where they're actually quoting Weinstein, the cluster heat map is well known in the natural sciences as one of the most widely used graphs in the biological sciences. As Weinstein notes, for visualization, by far the most popular graphical representation has been the clustered heat map, which compacts large amounts of information into a small space to bring out coherent patterns in the data. Since their debut over 10 years ago, this was in 2009, clustered heat maps have appeared in well over 4,000 biological or biomedical publications, and many thousands more after that. And so one of my goals in this course is to hopefully have clustering and cluster analysis heat maps really take a stronger role throughout education research and education data when it comes to education data scientists thinking about how do we describe the kinds of patterns and the pattern analytics and visual data analytics that we have across the kinds of data sets in that we have in education. So I want to show you an example of what cluster analysis heat maps can look like. So this is from a paper from me in 2010, analyzing the longitudinal K-12 grading histories of entire cohorts of students, grades, data-driven decision-making dropping out in hierarchical cluster analysis. So I'd like you to think about first hypothetical data. So this is completely made up data on just 8 students. And let's think about their non-cumulative course grades. So grades in every year, so their GPA, grade point average, but non-cumulative. So we recalculate it fresh and new every single year, not using any of the data from the year before. And so if you can think of some prototypical hypothetical students, listed here is by their student number from 1 to 8. So we've got some students who do really well. They're getting A's and B's throughout their time, K-12. We've got some students that experience quite a bit of challenge throughout their time, K through 12. And then perhaps we have a few students, some that are like student 4, who start high, but then fall over time in their grades. But maybe also student 8, who starts low and then rises over. So this kind of data you can totally graph when you have 8 students, but it becomes unwieldy and impossible once we get 100 students, 1,000 students, 10,000 students, 100,000 students. It's impossible to be able to see the individual data patterns and be able to discern any of the patterns overall and how students may or may not be patterning together across this type of longitudinal data using data that we collect all the time in schools. So with cluster analysis and hierarchical cluster analysis specifically, the first thing that happens is we reorder the list based on the similarity of the data patterns. So here you can see we've reordered the list based on hierarchical clustering, where in which students 3, 7, and 5 who have similar data patterns, they're going to now be reordered in the list so that they're right next to each other. And then students 6, 1, 2 are now distal, way down the list, far away from 3, 7, and 5. But students 6, 1, and 2 seem to be their own kind of pattern where they're near the bottom. And then student 4 and student 8 sit between these two sets of patterns. And so they would be in the middle. And so now with cluster analysis, you can, rather than have a student list of like alphabetical or by student number, there's just, we've reordered the list to be informative of the patterns. And then with cluster analysis, what you'll have is we'll create what's called a cluster tree or dendrogram. The dendrogram, because it looks like teeth, dendo, like dentist. But the people really call it a cluster tree as well, in which what the cluster tree does is the longer the horizontal lines, the more dissimilar a row of data is from a different a different row. So you can see, because the lines are very close together and short, for students 3 and 7, they're more similar to each other. And then student 5 is similar to cluster 3, 7. At the bottom, you can see student 6 and 1 are very similar to each other. And then student 2 is more similar to student 6 and 1 than anyone else. Student 4 and student 8 are very dissimilar to everyone else because you can see on the cluster tree, the line is longer, horizontal. And so through cluster analysis, we can not only provide informative patterning to this list, but we can begin to understand and see how these different patterns are clustering together, and how we can group students in an informative way using the data that we have available in schools. And then, again, these kinds of graphs, though, become impossible when you have lots and lots of students, thousands of students. And so instead, what if we replace the graph with a heat map? And so what we're going to do with a heat map is, it's a heat map. So red is hot in a heat map. Blue is cold in a heat map. So red means more. It's a heat map. So hot is more heat. So red is hot. Blue is cold. And so red is going to be a higher grade. Blue is going to be a lower grade. And again, and the reason, I'm not just making that up. This is the standard in cluster analysis heat maps. When you begin doing cluster analysis heat maps, please don't just choose colors that you like. There is a nomenclature, there is a standard that goes from high red to low blue. If you choose something else, it's going to be very confusing to people who know cluster analysis heat maps, and they'll ask you to flip it back around to the way it's supposed to be, to the standard practice in the literature. You would need a really good reason to change it. Also, don't use green and red because I'm colorblind, as our significant portion of the population. And if you use green and red, I can't tell what you're doing in your cluster analysis heat map. Well, what does a cluster analysis heat map look like? Well, if we replace each cell of data from the plot with a heat map, instead, this is the same data, just with a heat map. And what you can see is immediately the human eye is able to pick up these different patterns, these different blocks of color. And you can see that student 3 and 7 are very similar to each other, getting high grades. Again, a heat map, high grades, red is hot, high, and blue is cold, low, where students 1 and 2 are getting really low grades. So this, again, going back to this paper in 2010, I wanted to understand what were the patterns of hundreds of students across a few small school districts across their entire time in every subject in every grade, K through 12. And so what I'm going to show you is a cluster analysis heat map in which the x-axis is actually time, but also on the left-hand side, we'll have the cluster tree. So we're going to have 188 rows of students. And then in every single subject, in every single grade level, we'll have a grade. So what I went into, when I did this study, I went to the full permanent records of the students, K through 12, and their non-cumulative course grades in every single subject. And I ordered the subjects within every single grade level, from core subjects to non-core subjects. So starting with mathematics, English, science, all the way to physical education, computers, art, life skills. So every grade level, I've ordered the subjects the same in every grade K through 12. And so those are up in every column. So in this cluster analysis heat map, every subject is going to be a column. Every student will be a row, and their grade in that subject in that year will be a dot. And that dot will be a color from red to blue, where they're gonna, now the columns are gonna be z-scored, so standardized. So we'll talk about that in the next video. And they'll go from red to blue, high grades, red, high, hot, it's a heat map, to blue, cold, low grades. And no data, missing data, will be represented by white. So this is what it looks like. So this is 188 rows. And immediately what you see, again, red is high grades, blue is low grades. and white is no data. So first, we have two large clusters. A cluster at the top where students are getting generally high grades throughout their time, K through 12. And here I've put the distal outcomes, an annotation is what it's called, in which whether or not the students dropped out were outside the cluster analysis algorithm. But we put it on as a covariate so you can see how the clusters are related to these patterns. And the cluster tree is on the left. And so you can see that here, students in the top cluster, they generally get high grades because they're red, and they mostly graduate, where most of the dropouts are in the lower cluster, where students generally get low grades throughout. Now you can see these white streaks. On the left-hand side, the white streaks that come in are missing data where these students transferred in. So I didn't have any data on where they were before they came into these school districts, and so they were missing. Now, on the other side, they begin to become missing for these students. You can see where they drop out. But you can basically see pretty much where they drop out. Now, you might be asking yourself, do you have these contiguous columns of data? Well, recall, I'm ordering the subjects from core subjects to non-core subjects. And once you hit high school in the United States, many students have a lot of choice. And while you're ninth grade and 10th grade, you have a lot of core subjects to take. And the reason there's two columns is once we get to high school, I do semester 1 and semester 2, semester 1, semester 2. Then it goes core subjects to non-core subjects. And you can see that as these students who get the high grades, they're taking the core subjects in ninth grade and 10th grade, and then it begins to become more diffuse as they distribute out into the more non-core subjects by the time they get to 11th and 12th grade. Interestingly, you can see exactly that same thing happen here, but much earlier for the students who are getting low grades. So a few things I want you to notice about the cluster analysis heat map. First, you can see overall large clusters, but you can also see these smaller clusters, but all patterned in a way where we have every single individual student's patterned data for every single subject in every single course. So there's no averages here across students or across subjects. Every data point in the entire data set, like I was saying with Catel's data box, is here. However, it is comprehensible, in which we've got 188 rows by a few hundred columns. And with a cluster analysis and a cluster analysis heat map, we're now able to visualize the patterns over time. So let's take a little deeper look at each of these patterns. So, and including both the fact that we can see with these annotations whether or not a student dropped out or whether or not they took the ACT, which in the United States is for these districts, a good indication of whether or not the students are planning on going to college. And so if we look at specific subclusters, there's this cluster, the high cluster that I've labeled. These students, only one student dropped out. Most of them took the ACT, and you can see overall they get generally high grades throughout their entire time throughout these districts, K through 12, and also and pretty much most of the subjects. That's in comparison to this bottom cluster, the low students. These students start off getting very low grades in early elementary school, and this is where many of the dropouts are. You can see that, and again, the columns are Z-scored. And so you can see that these students are facing challenge from the beginning of their time in school. Low-high students are quite interesting. They're a fairly small cluster, and you can see that they start low in elementary school, but then rise over time. All of them graduated, and all of them took the ACT. And this is in comparison to the high-low cluster. These students, they start high, but then fall over time, many of them dropping out, and few of them taking the ACT. So if we look at the averages of these four clusters over time, the high students, they're doing really well throughout their time in school. And really everybody does well in kindergarten. But then once you hit first grade, things the variance starts to show up. And so the high is in comparison to the low students. And these low students, the ones at the bottom, they start low and then continue along. And you can see that they start to rise here at the end, only because students are beginning to drop out, the ones who are getting the worst grades. But then again, these really interesting students who are the high-low students, they start high and they look just like the high students. But these high-low students drop very quickly between grades 3, 4, and 5 into a pattern that looks almost exactly like the low students. And when I talk to a lot of elementary teachers about this, they immediately say, "Oh yeah, no, I know those students. Those are students who are memorizing words between grade 3 and 4 and struggle in that transition of learning to read to reading to learn." And so as they move into needing to read to learn, so they're moving to read books and really understand sentences, they really struggle. And it looks like these districts were really challenged for trying to help these students. But then one of the most interesting clusters is the low-high cluster. These students start low, but then again, there's a lot of variance. It's a very small cluster, but they rise over time. And so, like in my work, I'm in education leadership. One of the things I like to talk about when I use these kinds of pattern analytics is not only can we see the longitudinal trajectories of every individual student throughout their time in your school, but also we can identify clusters like the low-high cluster in which something worked for these kids. They were on track to be low, but just using this descriptive statistic in this pattern analytics, we can see just from non-cumulative grades, something changed for these students. So why don't we go talk to the students, talk to their teachers, talk to their parents, and find out what it is that helped these students, and is there some way that we can help the rest of the low students and the high-low students figure out how to join the high students and be supported through it. So that's an example of a one hierarchical cluster analysis heat map, just using grades over time, in which you can then see each individual student over time. And in the next video, we're going to get into the meat and heart of what and how cluster analysis and cluster analysis heat maps work. So I look forward to continuing the conversation in the next video. Thanks so much.